So on Friday, we started talking about Newton's first law, and we started talking about inertia. Okay? And we said that Newton's first law / inertia says that an object at rest will remain at rest. An object in motion will remain in motion unless acted upon by an unbalanced force. Okay? So what we said that meant was that this desk, okay, or actually let's use a chair, it's a better example here because it's got wheels. Okay? How many forces are acting on the chair right now? Two. Force of gravity and the normal force, or the force of the floor. Okay? They are acting in a force action-reaction pair. Okay? One is up, the other is down. They cancel each other out, so the chair doesn't move. Okay? What will it take to make the chair move?
Energy, no force.
Yeah, but actually both of those are true. Energy, because energy is required to do work. Work is force times distance. A force, an unbalanced force in this case, that would cause it to accelerate. Okay? Now, right now, the chair is moving at a constant velocity. Are there any unbalanced forces? There aren't. Okay? If I'm moving it at a constant velocity, it means that the force opposing me, which is friction, is balanced by the force I'm exerting on the chair. Okay? So it doesn't accelerate. Okay? Remember, Newton's first law also said that an object moving at a constant velocity will continue to do so until acted upon by an unbalanced force. Okay? So if I'm pushing it at a constant velocity and then I stop pushing it, it eventually comes to a stop because now what force is unbalanced? The friction of the floor, right? Or the wheels, the friction in the wheels, basically all kinds of friction, but friction becomes unbalanced and it brings it to a stop. It no longer travels at a constant velocity. Okay? And we're also talking about how this is a big deal if you are the occupant of a vehicle and you are not wearing your seatbelt. Okay? So if you are moving along at a constant velocity, like you would be, and then suddenly the car stops, you keep going because of Newton's first law. An object in motion remains in motion until acted upon by an unbalanced force. If you have a seatbelt, the unbalanced force is the seatbelt, and it leaves a nice rectangular shaped bruise across your chest, okay? And the airbag punches you in the face. I know everyone thinks an airbag is this nice pillowy thing that saves your life, but it literally punches you in the face. Okay? It explodes in order to inflate quickly. So it's not pleasant. And it'll leave big marks on your forearms if you're the driver, because it'll push your arms off of the steering wheel, okay, when it detonates. Okay? Has anyone ever been in a car accident with the airbags deployed? Okay, your ears will ring for days too, okay? Because it's like 100 and some decibels. Okay? The explosion that actually fills the airbag right in your face. Okay? So yeah, it's not gentle. It's not a pillow. It's, yeah, quite violent actually. All right. So inertia then is your tendency to just keep doing what you're already doing. All right. Now I think we talked about this on Friday, but what's the most important safety feature you can have in terms of reducing the injury you might sustain in a crash? Okay, seatbelt's pretty important. Definitely it keeps you in the car where you're definitely safer. Okay, but there's something even more important than that. Brakes. Brakes might prevent the accident. Let's say we couldn't apply those. The accident just happened. But yes, your ability to pilot the car and avoid an accident would certainly be an important safety feature. Mass. Okay? Mass is the most important safety feature in a vehicle because in a crash, there's a winner and a loser. Okay? Make no mistake, in every crash, there's a winner and a loser. Okay? And the winner is always the heavier vehicle. Okay? Here's why. In a crash, let's say we're looking at a crash between a smart car and a fully loaded B-train semi-truck. Okay? So an incredibly massive object and a tiny little car. Okay? Who wins in that crash? The semi, absolutely. Okay? Which vehicle has more force exerted upon it?
It's the same on both.
It's the same. Okay? This is Newton's third law. Every action has an equal but opposite reaction. When the smart car exerts a force on the truck exerts a force on the car, those forces are equal. Every action is an equal and opposite reaction. Here is what's different. So the force on the smart car and the force on the semi-truck are the same number. This number, mass, is not the same. Okay? It is your acceleration that hurts you. So your acceleration is the force you experience divided by your mass. Okay? So if you have very little mass, you're going to experience a very large acceleration. Okay? Here's the other complicating factor. Not over A, over T. If you are in the smart car, what's your final velocity going to be? Negative. Yeah, it's not going to be zero. The semi is going to keep moving forwards. That's because it's bigger and has more mass and experiences less acceleration. So the change it experiences in its velocity is a lot smaller than the smart car would experience, because it's going to go from 100 kilometers per hour to negative 20 kilometers per hour. Okay, it's going to go backwards. That's a big change in velocity. So most of the safety features in your car, okay, are designed around this variable, believe it or not. Okay? Your mass attempts to limit this variable. Okay? Every other safety feature in your car works on time. It wants to make the accident take longer. Why? Exactly. The bigger T is, the smaller A is, and that's what saves your life. Okay? So your seatbelt, okay? If you're in a crash of more than 50 kilometers per hour and your car isn't a total write-off, okay, you will have to replace the seatbelts, because the seatbelts actually stretch a little bit in a crash. Okay? Below 50 kilometers an hour, they're not going to, but more than 50 kilometers an hour, they're going to stretch. Okay? That helps to slow you down less violently than just hitting it. Okay? The airbag cradles your head. And one said it's not a pillow, it's a punch in the face, but it's a lot better than the steering wheel in your face. Okay? If you look at like your grandparents' generation, okay, anyone who was in a car accident had the same scar. And it goes right here. Because before airbags and before shoulder seat belts that went across, okay, if you got in an accident, your head went forward and hit this really rigid thing you used to navigate with. Okay? Because way back then, they were hard. They were wood or metal, or like metal encased in wood. They were hard. You would hit them and it would peel your scalp back. Okay? It give you a bad concussion, okay? And well, take a lot of your head off. Okay? So it was a bad experience. Modern cars, okay, not only have an airbag, but they have a collapsible steering wheel and collapsible steering column. So if you get in a crash, the whole steering wheel blows up in your face and then moves away from you, okay, in an attempt to keep you from hitting it. Okay, does that sort of make sense? Okay, they had, before airbags and they just had collapsible steering wheels, people would collapse their steering wheels when they got road rage. So they'd hit the steering wheel and the steering wheel would blow in, okay, because they were designed to do that.
Yeah, what about like bucket seats? Would those be like worse or better than crashes?
Well, the bucket seat positions you in a position where the seatbelt can work best. If you're on just a bench seat, that's like an old truck kind of bench seat, and you've only got the lap belts, it's not so much about the seat as it is about the belt. Well, those lap belts could cut you in half, right? Well, not literally, but they could cause you to have a major lower back injury, even possibly a spinal injury, okay? Just because you would fold in half over that one single point of restraint, okay? That's why they put the shoulder straps across so that your torso would stop moving, okay? This part of your body is designed to bear incredible forces, okay? Why put it on your pelvis, okay, alone? Because you would start to slide under the seatbelt until it caught on the soft part of your body, fold you in half, and cause internal injuries and spinal injuries. Okay? Having that three-point harness instead locks the belt over your pelvis where it's supposed to go, okay, and across your chest, so you can't slide under it, okay, but your body also can't fold you in half, okay, in the crash. So they're designed, all of those things, to slow you down gradually. Okay? Same with the crumple zones on your car. A modern car is designed to basically self-destruct in a crash in order to save you. You go back to the 70s and the 60s,
Those things
okay?
are built like tanks.
They're built like tanks, but the people that got in accidents in them didn't survive to pound out the dents, okay? Because the car wouldn't change shape. The car would just stop, okay? If you hit a tree in an old car, you can cut the tree down, okay? But now you hit a car, you hit a tree with a car, and it just, the car wraps around the tree, okay? That's safer for you, okay, in the end. Because if the car crumbles, that makes the accident take longer. Okay? If the car doesn't change shape, it just stops, and that time is much shorter. Okay? So all of these things are built into your car in order to make T bigger and A smaller. Because really, this is not something we have any control over. Okay? The change in velocity part of a car accident is not something we have control over. Okay? When the accident begins, that's our initial velocity. Our final velocity is hopefully 0 or positive if we're winning. Okay? But that's not something we have a lot of control over, other than having a great deal of mass. Okay? So, yeah, mass is important, and anything that can make T bigger is also important in terms of safety. Okay? Has anyone been in a car accident before? Okay? Like, it's not pleasant, okay? But I've been in a couple, okay? And I'll admit that one of them was my fault, okay? But in the end, the one that wasn't my fault was a left turn, like I'm going straight. This lady left turned in front of me in a little Ford Focus, okay? And my Expedition cut through that car like a hot knife through butter, okay? Like her airbags deployed, pushed her right through the intersection, okay? Like we continued to move forward. Our airbags didn't even deploy, okay? The acceleration that we experienced was so much less because of our incredibly large mass, okay, that we didn't have enough acceleration to deploy the airbags. We had to, put a new bumper on and replace the headlight assembly. Okay, her car was written right off. Okay, luckily she was okay, but she turned left in front of something moving that was heavier. Loser. Okay. So it's always the more massive vehicle that's going to win. Okay, now on that note. So, mass is important. Okay, if we're in a crash, mass reduces acceleration, and any of your other safety features reduce T, which reduces acceleration. Right? Because we can't do anything about force. Okay, if we can brake, great, then that can reduce our initial velocity at least a little bit. But okay, once the crash is occurring, that number is fixed. All right. So, what is force? Okay, we kind of have to define what a force is. A force is a push or a pull. Okay, so there's different kinds of forces. We're going to deal mostly with contact forces. Okay, so somebody is like pushing on a big box, or they've got a rope attached and they're pulling on a big box. Friction, which is a contact force. There's two surfaces and they're sliding past each other. Okay, the only force we deal with that's not a contact force in Physics 20 is gravity. Okay? Gravity is a field force. It doesn't have to be in physical contact with the object in order to exert a force upon it, which is why projectiles do what they do. Okay? If gravity only worked when we were in contact with the Earth, if we jumped, we would go into orbit. Okay? Obviously gravity doesn't work that way. The Earth has an area of influence over which its gravity pulls towards the center. Okay? Everyone all right with that idea? Okay. The other field forces are electricity and magnetism. Okay, those are field forces because they don't have to be in physical contact to exert a push or a pull. Okay, repulsion and attraction happen whether there's contact or not. Okay, now force is also a vector quantity, so we can see here with the tow truck and the car, that this force is directed at an angle. Okay, now if this tow truck is moving at a constant velocity, there's a lot of forces involved here. Okay? There's this force, which has a forward component okay, there's friction, I got the big okay, that's acting backwards, there would be gravity that would be acting down, and then there would be an upward component of the tension in the cable that would be acting up. If the car is moving at a constant velocity, then all of that stays the same because it's all balanced, and the net force would be zero. Okay? If the truck is at a stoplight and then starts to accelerate because it turns green, what will happen to this angle? It'll actually go out like this, right? It'll get a little bit bigger, right? Because the car's inertia is to stay put. The truck starts moving, and it takes a minute for that force to be transferred through the car. Similar thing happens when the tow truck stops. The car is going to get closer, so that angle will close up, okay? That's why tow trucks usually have like a solid thing that sticks out the back that actually goes under the wheels to keep the car from moving forwards when it's being towed, right? I don't know if you've ever seen this, but I've seen some pretty crazy stuff on the road. But I've seen one car pulling another car with just a rope. Okay? Why is that crazy? Exactly. Okay? It's essentially like tailgating somebody. Okay? There's no way for that car, I mean, even if there's somebody in it, because they would actually have to steer it too, okay, while being attached by a rope, and if the car doesn't run, how well do the brakes work?
Not very well.
Basically not at all, yeah, okay? So it's very difficult to get that to work.
Would the steering not really work?
The steering, well, it would be Armstrong steering, right?
Well, because your power steering and your
Exactly.
your brake oil and your power steering oil would not be
All in the
flowing.
same pump, right, so yeah,
So
that's why it's
yeah,
crazy.
Your braking, your steering would be basically non-existent.
Exactly, that's why it's crazy. That's why we wouldn't want to do it that way, okay? All right, so force of gravity continually pulls downwards, okay? We got pushes, we've got pulls, they're all forces, okay? And other than gravity, they're all contact forces, all right? Now, there are some things that we kind of mechanically have to also understand. Like this bulldozer can push on the brick wall. Can it pull it? Unless it's attached by a rope or a cable or a chain or something like that. Okay, if I put a cable or a chain on the bulldozer, can the bulldozer push? Yeah, you can't push on a rope. Right? I mean, it could if it just pushed the rope up against the wall and then pushed on the wall, yes, but you can't push on a rope. I mean, think about it, right? If you got a rope and it's tight and then you do this, all the rope does is go slack, right? A rope can only be used to pull something unless you roll it up and put it against it and then push, okay? But it doesn't work to push on a rope. It's my old high school physics teacher, that was what he said his contribution to physics was. Mr. Hill's first law of physics was that you couldn't push on a rope. Okay? That made perfect sense. Always kind of stuck with me. All right, now, the other part of Newton's first law is for something going at a constant velocity. Okay? And this is a concern if you are in a place where it's hard to exert a braking force. So if you're on an icy road. Okay, so I'm driving along and I see the light turn red and I press the brakes, but it's super slippery. I don't get to exert that backwards force. What happens? I just keep right on going. Okay, anybody ever had this one happen? You're trying to turn, right? You turn the wheel and you just keep going straight, okay, because it's that slippery. That's Newton's first law. Okay, an object in motion will remain in motion at a constant velocity. That includes direction, okay, unless acted upon by an unbalanced force. Okay, if there's not enough friction, well, then you just keep going straight into that thing you were trying to avoid. And what's your natural reaction as soon as that happens? Yeah, do all the things that you shouldn't do. Turn harder and push harder on the brake. Those two things only make the situation worse. Okay? It's counterintuitive. Anyone ever watch Canada's Worst Driver? Because they do this test on there all the time, right? They have the slippery thing with the styrofoam blocks, okay? And they have the person turn the corner and every single one of them pounds on the brakes, cranks the wheel and goes straight into the wall. Okay? And then the styrofoam blocks go flying everywhere. Okay?
She's supposed to like almost ease off the brakes to the point where you're not on them, and then
And reduce your steering angle, yes. Yeah, that's exactly how you do that. But it's counterintuitive, right? I want to turn, I got to turn harder. No, turn less and get off the brake. Okay? Because even anti-lock brakes on certain surfaces are just not going to cycle fast enough to give you that turn. Okay? If it's super icy, they're just going to go tick, 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 and do nothing, and you're just going to keep going straight. Okay? All right, so, got a couple videos of that. Okay, so, things to understand here, okay? Mass. We need to understand that mass and weight are different. Okay, mass and weight are different. Okay, your mass is how much of you there is. Okay, it's the amount of matter that you possess. Your weight is the force of gravity pulling on that mass. Okay, now again, this is a societal thing, but we always say, oh, I got to put on some weight, or I got to lose some weight. Well, you're not actually doing that. If you want to weigh more, just go somewhere else. Okay, similarly, if you want to weigh less, go somewhere else. If I go to the moon, I'll weigh 1/6 of what I weigh here, but I'm just as fat or skinny, okay, whatever, okay, when I get there. I haven't lost weight because I have the same mass. You can't lose weight. You can weigh less, okay, but you can't lose weight unless you lose mass, okay? So we have this idea that they're the same thing, like, how much do you weigh? I love it when people ask me that because I mess with them. Because it's a really rude question. Most people don't like it when people ask me that, but I choose it to be a learning experience. So if someone asks me, hey, how much do you weigh? And I tell them, I weigh 765 newtons. And then they chuckle awkwardly, shuffle their feet, and find someone else to talk to, which is totally all right with me because I'm actually an introvert and not very sociable. Yeah, it's a rude question. They should feel uncomfortable. You should never ask somebody how much they weigh, nor should you ever ask them what their mass is, because that's equally mean, okay? But that's what they want to know. When they say, how much do you weigh, you tell them in pounds or kilograms what your mass is. It's not your weight, okay? Does that make sense to everybody? Okay, weight is the force of gravity acting on your mass, not your mass. Steve, question?
Don't you calculate weight by timesing your mass by a gravitational pull of 9.8?
This is how you calculate your weight. Okay? Your weight is the force of gravity. Akira. It is your mass multiplied by 9.81, by the acceleration due to gravity. In fact, this is Newton's second law. Force is mass times acceleration. So the force required to accelerate something is equal to the mass times that acceleration. Okay? So that's why we can calculate the force of gravity that way. All right, so a massive supertanker obviously has a lot of matter, so it has a lot of mass. A penny has very little matter, so it has very little mass. Okay? It's much easier to accelerate a penny than it is to accelerate a supertanker. Okay? By the same notion, okay, if I've got, if I'm for some reason like crossing the street and coming towards me are a kid on a tricycle and a bus, I choose the kid on the bicycle. Okay? Right? Because I can step in front of them, put my hands out and stop them. They don't have enough mass to hurt me. Okay? If I do that in front of the bus, I'm going to be a foot ornament. Okay? Because it has way too much mass. Okay? I can't exert enough force to accelerate that mass in a safe manner. All right? Okay, so weight and mass, like you said, are two different things. So when you go to work out, you're not going to lift weights. You're going to lift masses. Okay? And I know that doesn't sound as cool, but it's physically right. Okay? The way we say it is just wrong. Okay? We always say it wrong. It's just one of those societal things that we do. Okay? Oh, pump some iron. Yeah, okay, say it that way. Because then you're not saying I'm going to lift weights. Because you're not lifting weights, you're lifting masses. You're exerting force against the weight. Okay? All right. So, for first law, okay, think of like hockey, or if you ever watch the, what are they called, the grass growing or paint drying, I mean curling championships, okay? Like curling is actually a really good example of Newton's first law, okay? If you get the rock going, there's very little friction there. It just kind of keeps going, Okay? If the ice was perfectly frictionless, curling would be a lot more entertaining. Because people would fall down all the time and the rocks would never stop until they hit walls.
Well, no, because even then they would bounce back
And then keep going the other way.
they just keep on going until the friction, like
But
the
there's no
absorption
friction,
of
so
the
they
energy.
infinitely go.
No, from the sides of the wall,
Yeah.
because you said the ice has no friction, but the sides of the walls would. So from their absorption and all that,
Eventually it would stop.
Air
Yeah.
But it
resistance
would.
too.
Yeah, and there'd be some air resistance, but I mean, that curling rock would go back and forth a lot of times if there was no friction on the ice. Okay, so once the puck or the curling rock is put into motion, if it's frictionless, I kind of need you guys paying attention. There's been a lot of talking going on back there. It's not cool. Okay, once it's put into motion, then according to Newton's first law, it should stay in motion. Okay, now in curling, you can turn the rock. Okay, how do we turn the rock? Yeah, you can apply a turn to it, an out turn or an in turn, okay, and you can make it spin, okay, but how else? Who else can turn the rock? The sweepers. Yeah, if you've got someone who knows what they're doing, they can steer the rock to an extent by sweeping. Because as the rock is going down the sheet, okay, if you sweep on this side of it, you reduce the friction on this side. And so it'll slow down more on the other side, and it'll actually turn this way. Because it's going to slow down more on that side and turn.
Isn't that why they like sweep to a certain point and then they let the friction from the?
Well, that's to get it distance, but if they actually also want to steer it, they will sweep more on one side
But
than the
I
other.
mean, like, so then, yeah, when you slide the rock,
Yeah.
they basically sweep it so then it goes a little bit farther than if they did.
Exactly, because when you sweep, what you're doing is you're melting the little beads. I don't know if anyone's ever been on a sheet of curling ice, but they take a hose and they spray it into the air, and then little droplets or beads of water land on the ice and freeze into little bumps. Okay? When you're sweeping, you're actually melting those little bumps with the broom and creating a thin layer of water on the surface of the ice, just like spinning your tire on ice does, okay? And it makes less friction, and so the rock will go further. Or if you only sweep on one side of it, you can actually get it to turn the other way a little bit. So these people need to know what they're doing when they sweep if they want to get that rock to where they want it. Okay? Does that sort of make sense? And that's what we saw with Woody, okay, floating off into oblivion, okay, or Homer, okay, hitting the experimental ant colony. Okay? There's just no, once you're going, you can't, if you can't exert a force in the other direction, you keep going. Okay? Okay, so this is Newton's first law, okay, right here. That's inertia, okay? An object at rest remains at rest. An object traveling at a constant velocity will continue to do so unless acted upon by a net force. And that actually should be velocity, because direction matters. It actually takes force to turn. Okay? What force helps you turn if you're in your car?
Your tire on your steer.
Okay, what force is between your tires and the road? Friction. Okay? It's the same if you're walking along and it's icy and you want to just turn, you have to apply a turning force in the opposite direction. Right? I push and I go this way. Okay? If it's too slippery, I slip and fall. Okay, instead. Right? I've got to have that friction there to cause me to turn. So it's actually a constant velocity because it would go in a straight line. Like what happens when we said if you're trying to turn and it's icy and you just keep going straight. Okay? That friction isn't there. All right? So in there, it talks about this, net force. Okay? A net force is the unbalanced force. Okay? That thing that's causing it to accelerate. If there's no net force, then there's no acceleration. Okay? If there is a net force, then there is an acceleration. Okay? And that goes to Newton's second law. Okay? And Newton's second law says that F net equals mass times acceleration. So in this case, I've got this book that's probably just being pushed along a table, okay? And it's being pushed this way to the left by 20 newtons and resisted by 18 newtons worth of friction. So what's the net force? 2 newtons left. Okay? So if I knew the mass of the book, I'd be able to calculate the book's acceleration, okay? Because I would know force and mass. Yes. Okay, so the net force is the vector sum of all of the forces acting on an object. Okay, and we're going to get into that, okay, as we go along into Newton's second law. Okay, we'll get into this whole idea. Okay, so we could have, let's say, a car being towed by a tow truck. Okay, so the tow truck would be exerting a force like this. Gravity would be pulling down. Normal force would be pushing up. Friction would be resisting. Okay, we would have all these forces, and we would have to find their vector sum. Okay, now if we think about it a little more, when a car is being towed, does it move vertically? So what that means is that the horizontal part of this force is this much, the vertical part is this much, so this plus gravity is 0. So we would only have the forward component of the tow truck minus friction, and we'd have our net force, and that's why the car would accelerate forwards. Okay? So there's a little bit of vector stuff still, obviously, in this unit. We would have an angle, and we'd have to calculate the sides and things like that. We're not there yet. Okay, just telling you that's what we mean. Okay, the net force is the vector sum of all forces. Okay, I could have drawn this as a vector diagram and gone like this, and then had like gravity and normal force, okay, and friction, okay, and this would have all ended up to essentially forward. Okay, I didn't do a very good job drawing that. Okay, all right. Okay, so a net force could cause a bicycle to pick up a lot of speed, but if that same net force was applied to a freight train, the resulting change would be almost imperceptible because the mass is so much bigger. Okay, but what that does say is that any net force causes an acceleration, even if it's small. Okay, so I could say that about the board. Okay, like if I'm just standing here and I'm resting against the board, the net force is 0. What happens if I push harder?
0.
I accelerate. Did the board accelerate? It did. You could hear it flex. Okay? Right? When I push it, you can hear it flex. Okay? That's an acceleration. It changed shape. It moved. Okay? It did. I mean, I did obviously move the whole wall. Right? What if I was pushing directly on the cinder blocks? They're probably not going to accelerate. Okay? I'm going to accelerate though, because they're going to exert an equal force back. When I stand on the floor doesn't accelerate, and neither do I. Okay? That's okay. If I jump, the floor doesn't accelerate, but I do. All right. So your inertia is directly related to / equals your mass. Okay? The more mass you have, the more likely you are to continue doing whatever it was you were doing before. Okay. All right. So that's what we just said. And again, inertia is the tendency of an object to remain at rest or at a constant speed along a straight line or constant velocity. Okay, so Newton's first law. We were talking about how important it is in terms of a car crash. But it's also really important in terms of how your seatbelt works, right? You've all had this experience, right? You're in a terrible rush, you get in the car, grab the seatbelt, and you pulled it too hard, right? And it locks. And then, in your frustration, you just keep pulling on it, and it's still locked, and you can't get it to move, okay? Until you just go, okay, and you let it go back in a little bit, and then you pull it out, okay? Now, the way a seatbelt works, okay, is that there's actually a pendulum. Okay, so just like my ghetto pendulum. Okay. So inside of your seatbelt is a pendulum. So if I'm moving along at a constant velocity, so is the pendulum, right? Okay, and I slowed down really slowly. I'm going to slow down quickly. Now, okay, so I'm moving along, and I stop. What happened to the pendulum? Right. That's how your seatbelt locks in a crash. When you're traveling at a constant velocity, this thing hangs straight down. But if you stop suddenly, it swings forward because of its inertia. And when it swings forward, it tilts the locking bar up so that it catches the ratcheted wheel and doesn't let your seatbelt unroll. Okay? When you're trying to get your seatbelt on too quickly, you just like jerk the whole apparatus violently, and then the thing locks into position because of that. Okay? But it's very sensitive, and this doesn't require any computers, sensors, or anything like that. This just works because of Newton's first law, and you can't stop that. So it's 100% reliable. Okay? Your airbags, on the other hand, work on a similar idea. They have an accelerometer. It's the same thing that your phone uses to decide which way you're holding it. Okay? So it's a cage essentially of wires and like a conducting ball or a gyro that's inside. When you turn it this way, it contacts the wires at the bottom and tells them they're holding your phone in the portrait position. If you turn it like this, the ball rolls and contacts different wires and tells it that you're holding it this way. You can also use it as an accelerometer. Okay? We actually, when we first got those carts, we actually did the same thing with our phones. We would just put the phones on the old carts, and you could use their accelerometers to send the data to the Sparkview. Okay? So what your airbag does is there's an accelerometer built into your car, and if your car stops suddenly and the acceleration is great enough, this ball moves forward, contacts the wires, which closes the circuit that detonates the airbag. Okay? That's why your airbag doesn't go off unless you achieve a certain amount of acceleration or going faster than 50 kilometers per hour. Okay? Does that sort of make sense? Okay? The original airbags didn't work like that. They were a contact switch. So if you got into a car accident, it would compress the bumper, which would close the switch, and then the airbag would detonate. But what that meant was, hitting the front of the car could detonate the airbag. Okay? There's actually this video, I couldn't find it. It used to be, it was like a meme for a while. This guy in a fancy convertible Mercedes is sitting at a stoplight, and there's this old lady crossing the street, and he's honking at her because she's taking so long, this poor old lady, and she just loses it. She takes her purse and smokes the front of the car with it, and the airbag goes off. Okay, it's like, that's karma. That's what that is. Okay, but that's not how those switches are supposed to work. Okay, back when they were contact switches, that's exactly how they work. So you could kick the front bumper of the car and set off the airbag. Okay, that obviously was not something they kept in play because it wasn't functional. Okay?
I mean, it wasn't functional.
Well, it wasn't.
Revenge on someone who was a total
But it's not the way it's supposed to work. You don't want it going off when it's not necessary. Okay, so does that sort of make sense? So that's an application of Newton's first law. Okay, you know what? That's what I've got for today, guys. Sorry, free body diagrams. Let's talk about this. Okay, so in this unit, instead of we'll still have givens, but our givens are probably going to look a little bit different when we're dealing with a problem. Okay, so what we draw in order to help us identify all the forces is a free body diagram. It doesn't have to be a nice picture like this one is. A free body diagram can just have a box. Okay, inside the box, write the mass. Okay, and then we draw all the forces that are acting on that mass. Okay, so in this case here, it's a car sitting on the road and it looks like it's braking. So we would have the force of gravity. We would have the normal force, and those forces would likely be equal, as you can see in this diagram. And then we would have our force of friction. Okay, in this situation, is there a net force? There is, because the forces aren't balanced. Gravity and normal force are balanced, but there's a force of friction that's not balanced. So if I drew a vector diagram, okay, that would be gravity. Okay, and this would be normal force. And that would be the force of friction. Okay? So the first two forces canceled, but there's nothing to balance the force of friction, so there's a net force equal to the force of friction backwards. This car is going to accelerate backwards, or slow down, probably, in this case. Okay? So free body diagrams, super easy, but that's basically your givens for a Newton question in this unit, to be able to draw a free body diagram. Steve, question?
Wait, so theoretically then, if you were to, like, I don't know, brake hard enough, you would start going backwards
Nope.
because the friction force is
No.
higher than.
The way brakes work, they're only a force until the object stops. Friction isn't going to.
Because don't they, isn't it just your brake clamp, which is clamp the wheel?
Right.
And so if the wheel's not moving anymore, it kind of can't really like start
Right.
holding it back.
You're going to accelerate backwards, but you're not going to move backwards. You're just going to stop. Brakes cannot propel you backwards. Okay? They're a braking force. That's why they're called braking. They're not a propulsion force. Throwing your car in reverse, if it didn't destroy your transmission, would be a reverse propulsion force. Right? Okay, so tomorrow we're going to start into Newton's second law, which is like the next 2 and a bit weeks worth of stuff. It's big. Okay?